Good afternoon, everybody, and welcome to another Geo-Institute live stream. It is the final Geo-Institute live stream of 2024, and by default, that must mean that it is the final GEOSTRATA Extra of 2024. Good afternoon, everybody, and welcome. My name is Brad Keeler. I'm the director of the Geo-Institute, and again, welcome. We've got something great for you today. If you don't know anything about the Geo-Institute, after you watch this fine program today, you should head over to geo-institute.org, and there you will find out all kinds of valuable things about us, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society for Civil Engineers. Woo! And if you like what you see today, and I feel very strongly, as always, that you will, you should, of course, click like, subscribe, and get notifications. And if you do those things in that order, we will let you know every time we post something to the YouTube channel. It is, of course, nearing the end of the year, dear viewers, and for that reason, I must also tell you a couple of things. We are going to make a year-end GI video. As we do every year, you can submit your photos and videos of all the great Geo-Institute things you did in 2024 our way, and we will do our best to include it in the year-end video. And if you are so inclined, you are again coming up to the end of the year, you need to make those tax-deductible contributions. A great place to do it is Geo-Institute student programs. We are, of course, very excited that Jean-Louis Briod and Janet Briod gave us $500,000 earlier this year, and we are attempting to match that to permanently endow student programs. If you go to geoinstitute.org or any page on that site, there is a prominent link to enable you to contribute to the fund. And we have amazing thank you gifts, including pre-ordering your very own Ralph Peck bobblehead. Who would not want to do that? So with that stuff out of the way, we have a first-time host of GEOSTRATA Extra today, which is very exciting. We'll get to her in just a moment. If you haven't looked at the current issue of GEOSTRATA, you can head to readgeo.com and check out the article that we are talking about today that was called, I should have gotten the title before we started, I believe, was it Managing the Data Deluge from the North? Did I get that? Perfect.
Or take a word, yeah.
Now, with no further hesitation, here to tell you what we're going to do today with her wonderful Santa hat on, it is Editor Gizem Bozkurt, GeoStrata Editor Gizem Bozkurt. Gizem, thank you for doing this. We're going to have a good time today.
Yeah, I'm sure we will. Oh, okay. Hello, everyone. Welcome to the latest edition of GEOSTRATA Extra, featuring an article from the December-January issue, as Brad mentioned, which is Team QC/QA Construction Database Management. I'm Gizem Bozkurt, Senior Engineer with Geo-Institute Consultants in Atlanta, Georgia, and editor of GeoStrata, and I will be your host today. And it's my pleasure to introduce and interview Jamey Rosen and Dr. Michael Arnold about their article, Managing a Data Deluge in the North, which was published in this issue, and today we will be talking about this. Jamey Rosen is a senior principal geologist and data manager with Geo-Institute Consultants. He serves as the data manager of record on several U.S. Army Corps engineers construction projects. Jamey developed the original wall tracker software used on U.S. Army Corps engineers' cut-off walls, and has spent over 15 years of his 25-year career focusing on data management of foundations, dams, and other infrastructure. Dr. Michael Arnold is a chief engineer for Bauer Foundation Corp, located in Odessa, Florida. He worked on numerous deep foundation projects involving techniques such as soil mixing, jet grouting, slurry walls, drill shafts. Michael is a member of DFI, Structural Slurry Wall and Seepage Control Committee, and has authored more than 30 technical papers. Welcome, Jamey. Welcome, Michael. How are you doing?
Doing great. Very excited to speak to your membership today.
Yeah, thank you. Thank you for joining me. Before I forget, let me also mention this. During the interview, if you have any questions for Jamey or Michael, please type them in the comments while you watch, and we will do our best to address them. Okay, let's get started. My very first question for those who is not familiar with the project or didn't have an opportunity to read your article yet, can you please briefly describe the Moose Creek Dam Rehabilitation Project in terms of what deficiencies had to be repaired and what remediation measures were employed?
Yeah, thank you very much for this great question. So I want to use that to give a little introduction here to the project. So this project, Moose Creek Dam Rehabilitation, is located in central Alaska, right outside of Fairbanks. So the owner is the Army Corps of Engineers, specifically the Alaska District, and it's a dam with a length of 8 miles. Just to give you some impression what the function of this specific dam is. So this is a flood control structure. We are here in the Tanana River, Chena River floodplain. We have Fairbanks here to the west, and then North Pole, very fittingly for the season. The location of Santa's workshop here in North Pole, then a little bit east of that. And in that floodplain, they had repeated floods through Fairbanks based on the Chena River. So that triggered the construction of a barrier wall that essentially in flood situation would divert the Chena River to the Tanana River and bypass the local flood flow. This structure, the Moose Creek Dam, was built in the 70s and completed in 1980. Usually it's a dry dam, it's just flood control. However, if there is a flood, then this is very important. So there is one structure here, the so-called control works, which control in a flood situation, the flow through the Chena River, just to give the right amount of flow that the city of Fairbanks still can take, and all the other water in that situation is impounded and ultimately diverted. The Moose Creek Dam is a zoned embankment dam, and based on the materials that are prevalent in that floodplain, it's mostly built of very coarse materials, so a lot of gravelly sand. The design of that structure relied heavily on a silt blanket on the upstream side of the dam. When they initially impounded that structure, or when the first flood event occurred that resulted in an impoundment, they immediately realized that there was some problems with this dam. They had sand boils downstream of the dam body that you can see here on the left-hand side. And consequently, the Army Corps installed in critical areas where those boils were observed, they installed here relief wells, sometimes really close to the tow trench, sometimes downstream, a little further downstream, based on the location of a road that is on the downstream toe of the embankment dam. However, they still struggled somewhat. The relief wells were producing a lot of sand in an impoundment situation, so a risk assessment was done in 2014, and different failure modes were investigated. Two very critical ones were the backwards erosional piping with horizontal or vertical exits, And we see that here that water would stream underneath the embankment and exit then on the downstream side, and consequently, based on high gradients, then erosion would start and would gradually work its way back to the upstream side and could potentially then cause a collapse of the dam on the upstream side. So in 2014, they classified it ultimately as a dam safety action class 3, which indicates moderate to high risk of failure. To address this, centerline barrier wall was designed by the Corps here, and subsequently the Corps started implementing the solicitation of that upstream barrier wall. Then in 2021, ultimately the project came to the market, had its funding was released, and the barrier wall was installed by means of deep soil mixing. So that was something the Corps decided that this was the right method to implement here for this structure. And ultimately Bauer was successful in the solicitation, and we installed the majority of the barrier wall here with single column mixing, essentially deep soil, simple deep soil mixing technique as a secant wall. So in a wet and hard sequence, so we install first the primary columns like we see here in blue, and then follow up secondary columns to close that out and form the full wall. So this is essentially the background for that project. Bauer has just completed these works in August, end of August, beginning of September of this year. And we were working with 2 drill rigs out there.
Thank you for providing very informative project overview. Yeah, it was very good start. So how did you both actually become involved in this project? What were your project roles and responsibilities?
I feel like the contractor should speak before the sub on that sequence. So Michael.
Yeah, so I mentioned that the Corps in 2014, they had this classification. They then started their design phase, and my involvement actually started in 2016 when the Corps reached out for the first time to seek industry input. So they had 2 more question and answer sessions with contractors in 2018 to 2020. So that means for me, this was actually the project where I was involved for the longest time, even before it came to the market. Usually, as I'm on the contractor side, we get involved only once the solicitation is out. So later for that job, I was then involved, of course, in the tender phase. I spearheaded Bauer's technical proposal and also was quite involved then after the award in 2021 to get the job up and running. And that means high involvement in all the pre-construction activities, especially on the pre-construction documentation. And to this day, as I'm the chief engineer here for Bauer, I am responsible for quality, and so I have constant involvement for that. And in this role, I also brought Geosyntec in, and especially my dear friend Jamey.
Oh, thank you. True. You mentioned the pre-construction submittals. That's about our starting point. So aside from all of the innovation, the value that we like to bring, the bottom line of where a sub like us would get involved is this, the specification. So in modern Army Corps rehabilitation projects, especially those that have subsurface construction, there is often this data management spec. And among other things, the spec requires that the contractor provide a formal data manager that meets certain qualifications, those referencing education and history on similar projects and credentials, et cetera. And then this data manager, who turned out to be myself, is then required to submit some pre-construction submittals, namely a data management plan, and this is on the critical path to construction. So the contractor needs to, first of all, submit quals for a data manager, and then once those quals are accepted, they need, through that sub, to provide this data management plan that details all of the work that will come, that we'll be talking about today, involved with collecting data, submitting it to the government, visualizing it through maps and drawings, etc. So to answer the question of how he got involved, it's because of the data manager credentials and the data management specifications.
Hey, Michael called you as friends, so I assume you two has a long connections. How did you meet?
We do. Yeah, we met originally in 2008 on another fairly similar barrier wall around the Herbert Hoover Dike, around Lake Okeechobee in Florida, another Army Corps project that far precedes any sort of formal specification. And I think Michael and I are both very proud of our longevity with our specific companies. We tend to stick around for a while. And through the years, we've met up again and again and co-authored articles for magazines and technical publications. And we've also both served on the Deep Foundations Institute committees. Wherever there's a barrier wall and an owner that requires specifications and Bauer gets involved, we like to think there's a space for us at Geosyntec as well.
Very good.
Yeah, with Jamey, we have known us so long, and I think always, I credit Jamey with introducing me to GIS. So that's something that I did not know in my prior career. And when we started working on that, he explained to me what GIS is and what data management is. So he really contributed also to mine.
Back at you. I learned everything about foundations from you. So this is a good time to define GIS. GIS stands for Geographic Information Systems, and it's a series of tools, methods, and software that deals with spatial and geospatial data. So it's a type of data management tool that can analyze and visualize data in a spatial context, and it's a very useful technology in construction, as hopefully you'll see from the article. And to be clear, Michael and I are speaking as if we're the only people involved in these, but of course we have several colleagues and teams, and I've got a long-running set of colleagues in Geosyntec consultants that have computer programming and geography skills and data management and data science skills, all of which come into these projects.
Definitely a team effort. So today we will be mainly talking about the data management, as we initially indicated the theme of this issue. And in your article, you indicated that this project will generate a huge amount of diverse data, and therefore data management will be crucial for the success of this project. Can you please elaborate on what kind of data parameters were generated and collected, and what Army Corps project requirements had to be met?
Yeah, so there was a quite extensive quality control program based on also the acceptance criteria and other specification requirements, and also actually a lot of things that we do anyway as Bauer whenever we install deep mixing elements. So for that project, and I will explain this essentially along the process as we go through the different stages to install the barrier wall. So it all starts with the slurry, and we start here with bentonite slurry. So for that bentonite slurry that we mix and let it hydrate, we determine the density and marsh viscosity twice per shift. Then we mix this bentonite slurry with cement and admixtures and create the binder slurry that we are ultimately mixing into the ground. So for that pre-placement, this is a term that the Army Corps likes to use here. For that pre-placement slurry, we also measure density and marsh viscosity twice per shift, along with temperature the same way. But I should mention here that we are using automatic mixers, which are equipped with digital recording facilities. So every batch, all the component weights are automatically recorded and give us also the first data stream. Then an important part of the QC process is actually the wet bulk sampling. So that means after we have installed the element, that means after we have mixed binder slurry with soil, then we go in and we take material from the wet column. And per the specification, we do that every 250 feet. And then at each location, then we take samples at 3 different depths, so top, middle, bottom, third. And for each sample, temperature, unit weight is determined. And then cylinders are cast, specimen are cast, and tested in the lab then for strength at 7, 14, 28 days, and permeability at 28 days. I highlighted or emphasized here the 28-day UCS and permeability, as those are actual acceptance criteria. Okay. Furthermore, the installation process itself is heavily instrumented, so our drilling rigs are equipped with a Beatronic system which records essentially all parameters every second. And this is also data that makes it, like all the other that you see here, into the data management system. So especially the focus is depth here, it's slurry flow and volume, and also verticality. So we deployed here a special verticality tool inside our drill strings, and we measured verticality at 3 different depths. So at the very bottom as we withdrew, and the bottom quarter point and the halfway point. And that's very crucial because that gives us the actual as-built geometry at depth. And this is then used to demonstrate by analysis, and Jamey will speak to that soon, that we have overlap between the elements, and that we at any point of the wall, along the wall alignment and at depth, have the required wall thickness. The last part of that quality control program is the verification. So verification borings are done, so core borings are done every 250 feet inside the hardened wall, so around 25 days age. Sometimes conditions up in Alaska are not always perfect. That varies sometimes. And we take cores. Then inside the core, inside the borehole, we run OPTV, so optical televiewer, to generate a virtual core. So this is what you see on the left-hand side here, and also determine borehole verticality with that tool. Then there is CCTV, so real video in a pump down condition, and we do in situ falling and rising head tests. So it's done in 2 stages, drill halfway down, essentially to about groundwater level, do a falling head test in the borehole, then drill to final depth and perform a rising head test in the borehole. Furthermore, from the course, as per the specification, there was UCS testing, 3 samples per core on the QC side, 3 samples also for QA for the core themselves, and the same goes with permeability. However, coring was very challenging in the conditions up there. We have large crevice, and with the specified strength, this is not concrete, I have to say. So we are talking here about material in excess of 200 psi. Then those cores are not always retrieved in the perfect way. Actually, sometimes there is no core retrieved, and therefore this sampling is a little bit problematic under those conditions. However, for acceptance here, the in situ falling and rising head test is what the core ultimately relies on.
Yeah, so you mentioned huge data. That's the huge data. But in the data management world, when we talk about the size of data, what actually matters is not so much the number of records, but the diversity and the variability of the data. So each of those items that Michael described has its own set of verification and validation requirements. It has its own home in a database. It relates to other data spatially, and all those relationships and individual data handling methods is what makes this huge, to your word.
Yeah, so since you have the floor now, Jamey, can you please describe us what is the information management system, IMS, developed by GeoSyntec, and what makes this system actually applicable to the specific needs of the Moose Creek Dam project that Michael describe us?
Yeah, so I'll do that with the help of this data flow diagram here. So an information management system is just that. It's a system. It's a bunch of different tools working together and a workflow that enables them to be interoperable in that way, rather than it being, one piece of software that is just deployed. So the specifications require, for example, that documents be stored in a secure file transfer protocol, an SFTP site, whereas another project might use OneDrive or some other proprietary way of storing documents on site, or sorry, on the web. So the information management system is this collection of the right tool for each job. So here we have Bowers rig with the Beatronic system collecting that data every second, and we stream that from Bowers Cloud into our database. We have documents that are collected, drawings, etc., that are stored on an FTP site, and virtually everything goes into this centralized enterprise database. So this is a web accessible, formal, documented database with tables for every type of data and relationships between those tables and rules for what type of information is allowed, and verification checks to identify data that is likely incorrect or a typo or out of spec or something. And we have a little extra components of the database. This actually fits inside here, but we'll separate it for visual purpose. This is the geodatabase. This is the storage for map elements and spatial elements that would eventually be served to that geographic information system. So everything in the IMS is about getting data into the database, organizing it, analyzing it, and then sending it out of the database into things like reports and drawings. We're big proponents of automating reports and automating as-built drawings, partly for the efficiency and the time savings, but mostly for that consistency and that security that the drawing has no choice of showing what is actually in the database. We serve data to a dashboard. This is the owner's specified requirement of how they can see the data in near real time. And we also serve the data in a much more raw format so that the owner can do what they like with. So this is a big part of an IMS. We have the user-friendly tools, the buttons, etc., but also the raw data that can enable analyses and reporting and quality assurance that is out of the contractor's hands. Right. So again, this is designed entirely to meet a specification, but also to meet Bowers' specific needs. So for example, I mentioned these as-built drawings, which are not technically part of the data management spec. They're part of a CAD spec. But once you go through the trouble of building a database and building a GIS, it's a fairly trivial add-on to send that data out to a formal drawing and have these updated in real time so that every night they're available for submission without the degree of manual effort that might otherwise be required.
Very cool. But I guess my follow-up question is, the IMS a user-friendly tool? Can anyone working on the projects access and generate plots, table, or the drawing that you shared with us? Or do these people need a special training?
Yeah, so the answer to should you build something user-friendly or build it just to be raw tables of data is always both, because one always needs to both visualize the data and be able to analyze it. So we do have the user-friendly tools. We have web-based viewers and desktop GIS software that we know the government has installed and can use. So this is the interactive profile view where one can click on panels or other elements and bring up the associated documents and look at the geology and see where quality control samples have been taken. Because it's a barrier wall, it's really a subsurface three-dimensional problem. So although we have pure three-dimensional viewers, the much more user-friendly way to interact with this kind of data is in a profile view along the stationing like this. You can see the geology and what's been installed. And in a planimetric view where we can see the elements on an aerial photo and show the locations in a plan view space. So this is user-friendly, but there's only so many buttons one can add to identify every single type of analysis that might be performed, so we don't even try. Next to this data, and you can export, from here to Excel and that kind of thing. But every night, we also provide raw data in a database. This is Microsoft Access, which is a desktop database tool that I'm sure everybody on this call probably has installed already. This is actually an older method. On some other projects, we simply provide text files, CSV files, for even more of a raw approach. But if the answer to your particular QA need on a given day doesn't have a dedicated button because it's highly specific to today's questions, you can always just access the data, sort and filter it, write a query, etc. And this is really important to the government, and the reason why this IMS was so applicable, because it's very focused on the organization of data to be useful, but then exporting it in a simple tabular way that can be analyzed from there. So it's both. As far as the special training, that's a great question. For something like this, it's my hope that most people who are familiar with, geological vocabulary and engineering concepts can open this and immediately see, oh yeah, I can zoom in, I can zoom in further, and clearly clicking on a layer will turn it on or off. I think this would be either immediately available or require very little training. But then when we leave kind of the user-friendly executive summary approach into the more raw data, that's where training is required. And there'd be two types of training. You need to understand how to work with a database, how to create simple queries, and the differences between this and something like Excel, which people might be more used to. And then there's the training in the subject matter, the geotechnical expertise to understand that, yes, although you can take the average of, say, depths that might not be so meaningful compared to the average compressive strength around a single depth over a range of stations. So, there's certainly the engineering training as well that we would encourage. Great question.
Yeah. Thank you for the detailed answer. So maybe it's time to do a demonstration for our viewers, because I'm very interested about seeing how things are working. So let's say I'm a project manager for this job, and I would like to know how many wall elements were installed last August 2024, and what excavation techniques they include. Can we quickly check with the IMS tool?
Yeah, absolutely. And I'm not sure of the delay in in the live stream. So we'll do it like this. So there actually wasn't a lot happening in August of 2024. We were pretty much wrapped up by then. So I'm gonna pretend you asked about August 2023 instead. So this is one of our dashboard views. This is what I think of as the executive summary. It's a little bit of a plan view, so you can see where you are along the wall. Profile view over that same range of stations. So you see some exploratory borings, and were this 6 months into the project instead of the very end, you would see some of the layout defined and a smaller amount of as-built elements defined, and a lot of blank space just waiting for the rigs. And here's some tables of quality control data. So let's do this. We're going to open the filters and select a range. Let's switch to 2023 and find August. So if we're looking at the entire month, if pretending the month was a pay item and Bauer wants to know what was done in that period, we'll do a simple start and end date over August. And then this will filter the data. There was no QC data in that time, but this is the SCM elements installed during that period. And everybody always asks, can I open an Excel? Yes, you can. Again, the raw data is really key. So by selecting a date range and by simply filtering a database, which is essentially what we're doing here, we can drill down, no pun intended, we always say that, to the elements installed just within that period and see that they're all of the SCM technology.
Okay, maybe a follow-up question. Can we also check whether the installed elements overlap sufficiently to prevent leakage? Michael, when he first started with explaining the project, he walked us through about how those columns are being constructed. Can we check it?
Do you want me to take that, Michael?
Yeah. Sure.
Okay, sorry, I thought you were
Go ahead.
suggesting maybe I missed the memo. Yeah, absolutely. So let's go back to here. Overlaps is probably the ultimate use of this tool. It's the calculation that requires the most inputs. You need to know the positions of the drill rig, the positions of the layout of the elements, and analyze the data coming off of the drill rig in Vtronics. And there's a few ways we do this. So let's look at sort of a traditional diaphragm wall shape, these rectangular elements. You can see we have this colored, the green and the brown here represent the layout, so the ideal perfect position of these panels, which we usually show at surface. So this will be the design. And then at any given elevation, we have the footprint of what was actually installed based on the positional information coming from the drill rigs. So here we have one element, primary, that is a little bit offset in this, maybe the upstream direction. This one is a little closer to the layout, and this is an order of millimeters, inches, so it's quite vertical. Don't be fooled into thinking we don't have a vertical wall here. And you see that we've done a little spatial analysis, really just an overlap, and we've color coded just where the two panels intersect. Mm-hmm. And then there's a few ways of measuring this. We could take the area, but the specific specification here is along the diagonal. So we can find just through geometry calculations, so high school type trig, we can identify this corner and this corner and take the distance across. And because this is color coded green, you know that this number is greater than the spec. And this happens at every single depth, so the top, middle, and bottom, because that's what we've analyzed in this project, although it could be every 6 inches or something. And it happens at every single intersection along many miles. So one can, look at a drawing of just a specific station range and see that. Or again, we always go to the raw data. We can look at our overlap details table and find for any given combination of elements or any given station range, etc., we can look at this diagonal value and find any that are outside of spec. But they all, if they were outside of spec, there'd probably be a remedial activity. So by the time the project's done, everything is expected to meet the spec. Hope that answers the question.
Yes, it does very well, actually. Thank you. So we talk about how project teams can use this tool, but can you maybe also elaborate on how U.S. Army Corps is using this tool with their own data?
Yeah, I'll comment on that. This is my favorite part, because the answer by design is we don't know what they're doing with their own data. And this is very important, because if we provide a platform that they can use for their own analyses and we provide the contractor data, they can do whatever they want on the QA side without any bias, without any fear that we're cooking the book somehow, because it's all done on their side. So in addition to these web viewers and database files, the spec allows us to send what they call the fully editable GIS. This is desktop GIS software, ArcGIS Pro, that some of you listening might be familiar with. This is all by definition the exact same data that goes on the web and the exact same data that goes in the database, because it all comes from that central enterprise database into all these different things. But every night, this is updated with the latest data. So the latest verification borings that might have been installed, any new quality control data, any VBs that have been installed, as well as their geology and their access to their documents. Again, in plan and profile view. And this whole thing is packaged up into a single file, sort of like a zip file, but a GIS type, and put on the SFTP site. And anytime the Army Corps wants to do their own work, they will download this file, and they can click Add Data and add QA data that we don't have, or they can add CAD files that they may have developed that we don't have access to or aren't aware of. They could add their own geology that they haven't sent to the contractor for one reason or another. And they can run analyses that compare the QC to the QA data, which is, a primary function of the QA program. Or they can use this once the project's done as maybe a platform to design the next phase of work, if there's something else to be done at Moose Creek Dam that we're not aware of, or at other projects that Michael and I have worked on. This sort of tool has been a big part of the internal Army Corps post-construction review. And ultimately, we hope it will contribute to that DSAC change in classification. So what they do with it is entirely up to them. We just make sure that the data that the contractor collected is correct and organized and documented in a usable way. Thank you.
So maybe switching the topic a little bit from IMS to this QC/QA effort. Can you help us to visualize what level of on-site and remote staffing was needed to support the QC/QA effort for this project?
Yeah, on the quality side, the staffing really depends with our projects whether we are acting as subcontractor or as prime contractor. So here for the Moose Creek Dam job, we acted as general contractor, and for every Army Corps of Engineer job, there is the head of the quality control system is the quality control systems manager. So we have that position. Then as the works were carried out day and night, we have a QC engineer for deep soil mixing activities here, one for day, one for night. And as we were acting as general contractor, we also had one additional engineer always there on the QC end for the other scopes, the civil works platform creation. There were a few other items in that contract. I have to point out also that the QC not only is based on, or this duty is relying only on QC engineers, we also have the slurry plant operators performing some QC tasks, of course, checked by the QC staff. So as the slurry mixing is pretty much automated, the plant operator will check that everything goes according to plan and we are within the range of slurry parameters that are specified or derived by the mix design. But for that specific data management scope, we always had one data engineer remotely working on that. So every day somebody would collect all the data, would feed in new design data for each element and process the rig data to produce reports, essentially running our internal side of the data management system.
Okay, thank you. And coming back to this database, since this project is complete, I would like to understand, can anyone still access this database for future use? It's like still available? If yes, will there be any cost associated with it, any monthly or yearly cost to be able to store and access the data in the future?
Right. So the answer is no cost as long as there is a new data being added to it. We talked a lot about the raw data being accessible and the Army Corps being able to download these packages. So once they've downloaded files from the FTP site, they have a complete offline archive of everything we've done without any need to ever call us again if they choose not to. And there's sort of a tenet of good data management is to be to future-proof the data to the extent possible and to make sure it's not locked into some proprietary system. So sometimes we'll get involved in a project from like 30 years ago and there'll be a file type that no one's ever heard of and it requires software that has long since been made unavailable because the company doesn't exist anymore. So by using, where we can, ASCII and other open source file types to make sure that the data is pretty future-proof, and if not, at least industry standard GIS file types and database types to avoid that concern that in 6 months they won't be able to read the data, let alone 60 years or whatever the scale these projects are on. The website will keep online for as long as anyone needs it because it's part of a larger software system that's being hosted. Eventually, when nobody needs it anymore, that'll be turned off. But there isn't a cost requirement or a business model really to host something that the Army Corps has already paid to have developed and paid to download.
Okay, good to know. Thank you. So my last question before turning the floor to you for any closing remarks. What advancements in data management tools have you seen during your career? You mentioned that 25 years, 15 years is heavily on the data management. Can you talk about this?
Yeah, I think it's been an interesting and exciting journey over those past 15 years. So back in the days, we started with everything being offline. So typically desktops system, there was already the internet, so we synced stuff. So for the old wall tracker system, now everything I see is online. We expect web-based system. I mean, we are so used to GIS in all aspects of our life to know where people are, where our tools are, where
your drill rig is.
Exactly. And what we see also is that we are generating much more digital data right away, so more digital raw data. So we have seen a lot of shift from 2D to 3D. We see digital twins arising. And also that contractors are doing more data management on their own. So for instance, Power has, as a group, implemented a digitalization group that just specifically focuses on digital data in the specialty foundation business.
Yeah, that covers a lot of it. So certainly the Internet of Things, this interconnectedness, rather than downloading data from some isolated tool or instrument or device, we now expect, or at least have the option for that device to send its data to the internet and automatically put itself into our databases and our tools to reduce that manual effort and increase the consistency. There's also been a shift to web-based tools versus software. You all probably know that it's almost impossible to install software anymore if you're part of our organization. So we tend to serve all of our tools, unless it's specifically specified to be offline, like I showed. Everything should be a web app, partly to avoid that IT requirement of the software installation, partly so we can control the security and the access to data, rather than just have a software tool out there that can be shared, but mostly to retain the ability to constantly keep things up to date. So rather than requiring someone to update some desktop software to be sure they're up to date, if they go on a website, it has no choice but to be up to date, because everyone's looking at the same data. And the patience for waiting for data has disappeared, as it should, because we have the ability to deliver things so quickly. Another big change has been the standardization of the database design. So what we call the schema. That's the description of the tables and what goes in those tables and how the tables relate together. It wasn't done on this project because these specs are actually like 5 years old now, but in even more recent specifications for Army Corps projects and projects by other owners, there's an attempt to require the contractors to populate a database that is consistent from project to project, and ideally hold data from multiple projects, so that we data analysts and the government, et cetera, can look at trends across projects, can compile all the data for a given site, even if different contractors were involved. So that standardization and better design of data is a big part. I guess there's a few more too. The field data collection, there's a movement away from writing in notebooks, although as a geologist, I still respect that, and to use mobile digital tools, so phones and tablets, partly to save time and have that data be available right away in the database, but mostly for that consistency. So, it's impossible to write something that's not a date into a mobile tool that requires a date being entered. So there's some data quality gains there. And the push-pull I'm noticing between applications and simply requesting data. So on some U.S. Army Corps projects, there's actually no requirement for any sort of software or visualization. It's simply give us the data every single night in this specified format, so that the owner, the government, can use their own tools, versus other projects which say we don't have any time or staffing to look at this raw data, so the requirement is entirely on the hosting and visualizing and analyzing side, and every combination there. That's probably enough progress for 5 minutes.
Thank you both. By the way, I see 2 questions in the chat box, so let me ask them one by one. The first one is from Carl Smith, asking, can you elaborate on how you obtained the second pictures on the quality control program slide?
Yeah, I think
the televiewer. Yeah.
So let me share my screen again. So I think this picture is meant here. So this is a picture of virtual cores. So essentially, it's a borehole camera picture, and it's just presented as coarse. So what we see here is actually a view from inside the borehole towards the borehole wall, now into different directions. It's now formed in a way that it, as if I'm looking to the core, say from the east, from the west, from north, and from south. But it's ultimately just derived from one picture. I can just put this over here. So that's the same, very same section here. It's just this one picture, and this is north. We zoom around, the middle is south, and then we are back to north as we go clockwise around the board. It's essentially the borehole picture unwrapped.
Yeah, and we often do put these geospatially located in those profile views, so you can see the photo where it belongs in the ground. But it's kind of funny because these are so detailed, you have to zoom in so close to make any sense of the image and to get any value of it that you lose all the context of all the other data layers. And GIS is so much about context, it's so much about looking at data and how it relates to other types of data, that you might as well just open the picture as Michael did and zoom in there to see the detail.
Yeah, and there is a lot of, well, you say there is an issue. You see some feature in here. You want to know, where is this georeference? Is this towards the outside of the wall, towards the face of the wall, or is it along the wall alignment? It might not be such big of a deal. So this has helped us in the analysis of quality topics quite a bit.
Thank you both for answering to that question. And the second one is asking, do you have plans to integrate with open ground data collected by geologists?
Yes, that is in there. So we have 2 database tables that I believe are direct exports from open ground. These are a table with the location of all geological borings, so the geometry in 3 dimensions, and the stratum table has the identified geology or stratigraphy from the borehole log. So I think that I say I think because this is sent not in as automated a way as the other data, but I think it's collected by a geologist and entered into the open ground software, which connects to the open ground cloud, which on many Army Corps projects is accessed directly by the government. So it doesn't even go through a subcontractor. They can see it right in that cloud. And then the raw data goes into here, which is important because our profile views show what we call the stick diagrams. So those vertical or angled lines in profile color-coded to each of the stratigraphic intervals, to each of the facies of the geology identified.
Thank you. I think with that, we answered all the questions from our viewers. And anything else you want to add at the last minute? Anything you want to share before I invite Brad back to joining us and he's here?
Yeah, I'll just share that more and more owners are requiring some type of data management. And as a result, I think, as a direct result, the technology that we use to meet those specs is getting much more cheap and much more available, and is no longer kind of the scary, highly sophisticated stuff that you need $1 billion project to do. And there are free generic specifications out there that any owner of maybe a smaller project outside of the massive Army Corps of Engineers can download and apply to get the benefit of these data management technologies.
Yeah, also from my side, I think this was an exciting example here of our collaboration, and I think it's very great times here to really see digitalization work its way throughout the construction industry. And I think here in Deep Foundations, we are almost leading in this field in construction, because everything that we do is kind of recorded. Thank you.
Thank you. Thank you both for joining me today. It was a very nice talking, both of you. We learned a lot from your project. Great information. Thank you. I guess before turning to you, Brad, I just want to wish everyone a very healthy, happy, joyful, successful holiday season. Happy holidays.
Happy New Year.
Thank you very much.
That's great. Thank you, Gizem, for doing a great job hosting today. Jamey, Michael, this was fantastic. And a little shill for GI's foray into data management here. Be sure for all of our viewers to check out the DIGS protocol. If you haven't yet, you can find out more at digsml.org. We just, while this live stream was happening, put up a new post in the DIGS blog on the GI website, so you can check out all the latest news in our effort to help the world standardize geotechnical data reporting. Sounds very grand when I say it that way. I will echo Gizem and wish all of our viewers and everybody in the community happy holidays and best wishes for a brand new year, 2025. Words I never thought I would say. When I saw some kid with a letter jacket in school that said 2000, I thought that sounded very futuristic. And now we're going to be 25 years past that. It's been an amazing year on the GI YouTube channel. This is our farewell until January. Be sure to go back and catch up on all the great stuff we've had over the year. Other episodes of GeoStrata Extra, Director's Cut, the Cross USA lecture, it's all here in one place. And if you liked what you saw, and as I say, you probably did because you're here at the end, you should click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. At the end of year 5 of GeoStrata Extra, we have to give a shout out to Jim Withiam, our chief editor, for being so supportive of doing this and helping us pick the articles every month. This particular episode was chosen by Christina Scott, our technical manager. She thought this was a good choice, so shout out to her as well. Our producer today was Aurora Flieger. And I think that's it. Everybody have Merry Christmas, Happy Holidays, Happy New Year. Our next live stream will not be until January 21st, and it's going to be our Geotechnical Frontiers sneak preview number 3. So you'll want to get registered for that and all of our other live streams on our Eventbrite page, and we will see everybody soon.